Molecularity. The word molecularity refers to the number of molecules that are involved in an elementary reaction. Okay, what's an elementary reaction? An actual molecular event, right? So a unimolecular reaction, okay, an elementary reaction that has a molecularity of 1, okay, so molecularity of 1 is called a unimolecular process. That involves simply a molecule that fragments, falls apart. So it involves just one molecule falling apart into two pieces, two or more pieces, or one molecule rearranging its the way rearranging the atoms within the molecule. Okay. Now, if you have a collision of two molecules, then you say the molecularity is 2. So the process we call that a bimolecular process. If you have three molecules involved, three molecules colliding, then that's a termolecular, as in ternary, tertiary, number 3, or trimolecular. Okay? Now, molecularity is greater than 2. Any step that involves a collision of more than 2 molecules are very unlikely. So when you propose mechanisms, you generally propose mechanisms that steps that involve only 1 or 2 molecules. Okay, so now that's what molecularity means. So let's consider the hypothetical elementary reaction. We have A plus A yields B. So would you call this elementary reactions? I'm telling you that I'm proposing this to be an elementary reaction. Is this reaction considered unimolecular, bimolecular, or termolecular? That's two molecules of A colliding, getting stuck together, and the pair that's stuck together, we call that B. No trick here. Bimolecular. Two molecules colliding, okay? And usually it's a giveaway that it's bimolecular, especially if it's written this way, because otherwise you would just say 2A yields. Usually when you write mechanisms, when you propose elementary steps, if you're to emphasize that it is a bimolecular process, even though you could have abbreviated this as 2A, you would write it as A plus A gives B, okay? So the number of molecules that's actually involved, if I tell you, it's called, will be the molecularity, even if they're the same kind. Okay, so the fact that I call this an elementary reaction, that means I'm telling you, I'm proposing that in this particular case, two molecules of A collide to give you a molecule of B. Okay, so that's a bimolecular step, a bimolecular reaction. Now, how is molecularity related to the reaction order? The reaction order of an elementary reaction is equal to the molecularity. So for example, if I say that this reaction right here is unimolecular, then if I propose that to be a unimolecular, an elementary reaction, then I would expect, if I were to go to the lab and made measurements, I would expect to find the rate law to be equal to K times the concentration of A. Rate equals K times concentration of A. It's going to be first order. So if the molecularity is 1, okay, then the rate law would be first order. If the molecularity is 2, what would be the overall order for the rate law? It's going to be second order. So for example, if I have two molecules of A colliding to form B, then the rate law would be rate equals K times A squared. It's K times concentration of A times concentration of A. If it's termolecular, and this one there's another bimolecular. If it's a bimolecular reaction that involves a collision of A and B, then I would expect the rate law to be rate equals K times concentration of A times concentration of B. Okay, so this is also, so this bimolecular reaction right here, okay, so this bimolecular reaction has a second order rate law. Why is this second order overall? Because it's first order with respect to A and first order with respect to B. So overall, it's second order. Okay? So if you know the molecularity, then you should know what the reaction or experimental order of reaction is. Okay? Now, but, there's a big but here. Your reaction order is experimentally determined always. Okay? You can predict what it would be if you propose a mechanism. But the only way to know for sure what the rate law is you actually do it in the lab. And we talked about that in the last lesson, right? So, it doesn't mean that if you find something that is second order in the lab, that the mechanism, it's an elementary step and it's bimolecular. It doesn't, the reverse conclusion doesn't work, okay? Because not every reaction is elementary, remember? So a reaction can be a series of elementary steps, and if you measure the rate law in the lab, it might turn out to be zero order, first order, second order. So the reaction order is really something you only determine in the lab. Okay? Whatever series of elementary steps you propose, it must predict a rate law that's consistent with uh, the observed rate law. So how are we going to do that? In general, like I said, if it's just a one-step reaction, molecularity will tell you what the rate law is. But if it's a series of steps, then there's something else you have to do to figure out, to predict what the rate law is going to be. And whatever prediction you make should be consistent with what you measure in the lab. Okay, so if I say the rate law is second order with respect to A, it doesn't mean that it's an elementary step, that it's a bimolecular reaction. It could be, but it doesn't have to be. So we're going to illustrate that with a few simple mechanisms, okay? But before that, let me just quickly check to make sure you got that. Let's say you have a hypothetical elementary reaction. Collision of two X molecules gives you Y and Z. What is the rate law for this reaction? Okay. So if you know the molecularity, you should be able to say what the order is, right? But if you know what the order is, it doesn't mean that you know what the molecularity is. Okay, not necessarily. So it, it doesn't go both ways, right? So this one is second order with respect to X. Okay? How about this one? What is the rate law for this reaction? 2I gives you I2 gas. Okay, you fell for my trick. I did not say that this is elementary. Since I did not tell you it's elementary, you don't have enough information. Okay? You can only predict the rate law given a chemical equation if you're told that that's an elementary reaction. This, in fact, is not an elementary reaction. Bond formation, we talked about this earlier. The correct answer here is C. Remember bond formation, in order for two atoms to get stuck in a bond, when two atoms are about to collide, okay, when they collide, they're just going to separate and not form a molecule, right? If they have enough energy to be separated to begin with, when they collide, they're not going to form a molecule. The only way they can form a bond if there's a third body that comes along and collides with them and takes that energy away from them. Combination of two atoms to form a diatomic molecule is in fact a third order process. Okay, so it's not, the rate law for this would be something like K times I times the I squared times the concentration of a molecule. That M right there would be total concentration of all the molecules in your system. Okay, so this is not necessarily going to, this is not an elementary reaction. If I told you that I'm proposing this to be an elementary reaction, then you say, yeah, then it would be A. Okay? So be alert to that. If it doesn't say it's an elementary reaction, if it's not obvious that it's an elementary reaction, it's not being proposed as part of a mechanism. So in other words, it's not being proposed as an elementary reaction. Don't assume that it is. Okay? So this one, you don't have enough information. About this one. 2NO2 plus F2 yields 2FNO2. This reaction is most probably A, an elementary reaction, B, a multi-step or complex reaction. All right, so what's the likelihood that you're going to see three molecules colliding? Not very likely, right? So it can happen, but it's not very likely. So most likely this is a multi-step reaction. Okay? So proposing a thermomolecular process as part of a mechanism is generally not a good idea. But if you have enough experimental evidence to say that that's what's going on, sure, no problem. But if you're going to propose mechanisms, chances are your best bet would be to go with a series of either unimolecular or bimolecular steps. So